We're going to take a look at a slightly new concept, is a function of several variables. Now the language gets a little weird here, kind of depending on the way you're looking at variables. So far we've looked at functions like this. Y was a function of x. And you could very easily say, well, there's several variables up there. You have x's and y's. So if you're interpreting the number of variables as just how many letters you have, in this case you would say that there are two variables in this equation. However, most of the time when you're talking about variables, you're talking about independent variables. So in this equation here, there's only one independent variable, so you could just as easily say that this is a function of only one variable. So kind of whichever way you look at it is what you're defining. However, we're going to look at today, instead of y is just some function of x, here we only have one independent variable. We're going to look at functions that look more like this. Like z, just our next letter, is some function of x and y. Now in this case we have one dependent variable and two independent variables. Again here x and y have nothing to do with each other. They're completely their own letters. And you can go up to as many different variables as you want. Generally w's and x. We'd have some function of x, y, and z. Now when we saw, if we just sketched a picture of this, this is generally a two-dimensional picture. Which means here, since we have three variables, this would be a three-dimensional picture. And kind of visually here, this one would be 4 dimensions. Now, unfortunately, we can't draw something in 4 dimensions, but you can very easily see why something like this would be helpful. Let's say we have a room, kind of like the one I'm staying in, and you wanted to know the temperature at every single spot in this room, right? So here's a function of 3 variables that would tell us the temperature at any given spot. So you may want to know, a function with 3 variables pretty often because we live in 3-dimensional space. All right, now we're defining these brand new functions. We need to go back to a lot of the things that we did in calculus, Calc 1, and even some algebra stuff like domain. Remember, domain are the values that you're allowed to plug in. Now, for whatever the function is, and it doesn't matter how many variables it is, it just gets maybe slightly more complicated when we're looking at functions that maybe look like this. What if I said 6 over the square root of x squared plus y squared minus 25? Okay, like always, you have to look at all the things that may restrict your domain. Kind of like here, we have an even root. Since we have an even root, we generally don't want to deal with complex numbers in this course. We're going to want to make sure the stuff inside there is greater than or equal to 0. However, since it's on the bottom, it can't be 0 either. So we have two things restricting our domain, the fraction and the radical. So I know x squared plus y squared minus 25 has to be strictly greater than 0. Or another way to think about it is x squared plus y squared has to be greater than 25. Now, that's actually your domain, which is a little bit more complicated looking than what we've seen in the past, but basically what you're saying here, in the xy plane, because this is where our domain comes from now, because that's what we're plugging in, we're looking at a circle of radius 5, right? And now we can't include the circle because it doesn't have the equal sign, so as long as we have any point outside the circle here, any point out there would work. So we can't use anything inside the circle because it's got to be greater than that. So generally you don't have to sketch a picture. Generally just something like this is pretty standard. So when you're looking for domain, again, you're just finding all the values you're not allowed to plug into that particular function. So if I were to give you something like, same question, like find the domain, the natural log of x minus 1. Pretty good parentheses around it. All right, so if we look at this particular expression, what would the domain of this be? Well, again, remember what the domain restrictions for the logarithms are. For logarithms, generally we don't want to take the log of negatives because that gives us complex numbers, and for this semester we're not really working that much with complex numbers. And we know we're never allowed to take the log of 0. So I know in this case that x minus y has to be greater than 0, or another way of saying this, x has to be greater than y. Now again, you could leave it just like this, but to think about it, this is the line y equals x. Now of course, we can't include that because it doesn't have the equal sign, so it's got a dotted line. And where are the y values less than the x values? Well, that would be in this region over here. So the domain, this function would be valid for any point any point you picked here below the line y equals x. So finding the domain, again, you're using the exact same restrictions that we learned back in algebra, somewhere back in algebra, but it's just you have a couple more letters involved. All right, now since we have more complicated pictures, and you can see that with the more variables we're going up in dimensions, how do we actually sketch these drawings? Again, the good news, generally I'm not going to grade you guys on being able to draw in 3 dimensions because it can be tricky, but there is a way to do a 2-dimensional sketch of this where you can get a basic idea of what it might look like. And here we're going to sketch this using level curves. Now, what are level curves? Here's the idea. Let's act like we have some 3-dimensional shape out there, so that's horrible. Try the same picture again. So this thing about this is just kind of a bowl here. And if it's sitting in our x, y, z plane, so it's just this 3-dimensional item, basically what we're going to do is I'm going to pick values for z. So I'm going to do like z equals 1, z equals 2, z equals 3. Now remember, if you just have z equals 1, that's the equation of the plane that cuts through at z equals 1. So you get this plane out here at 1. What would it look like as it cut through this shape? Well, it would cut through and make kind of somewhat of a circular shape as that plane cut through there. So that's really low though. All right, so you kind of get the idea. So what we're looking at is we take these different z values, we're just cutting it across. So let's see. Sketch the level curves for, let's do z equals, let's do the square root of 9 minus x squared. Let's do minus y squared. Okay, so looking at this, and if we wanted to sketch it, generally they're going to give you z values. Let z be equal to 0. Let z be equal to, I don't care, 2. Let z be equal to 3. All that kind of stuff. So they're generally going to give you z values. So let's see what happens when we plug these in. Okay, so at z equals 0, we put 0 in, so this is basically what this looks like as it crosses the xy plane. We get the square root of 9 minus x squared minus y squared, which here, if you square both sides, 0 equals 9 minus x squared minus y squared, or another way to write this is x squared plus y squared is equal to 9. All right, I'm going to go over here real quick. And I'm just going to draw the xy plane basically. Now I'm not going to put xy in there, even though those are the directions that we're talking about. Yeah, but so you can kind of see. So for the first one, this was with z is equal to 0, we get a circle of radius 3. Now on this, you're going to want to write z equals 0 right there. So you know that's what it looks like as it crosses the xy plane. And then you do it again for some other values. So let's do z equals 1 real quick. So if z is equal to 1, your 1 is equal to the square root of 9 minus x squared minus y squared. And you do the exact same thing. Square both sides. 9 minus x squared minus y squared. Move everything around, and what would we get? We get x squared plus y squared is equal to 8. Okay, so again, this is a circle of radius 8. So about 2 square roots of 2. So somewhere in here, so at z equals 1, we'd have another circle. So this would be about z equals 1. If we did z equals 2, 2 squared, 9 minus x squared minus y squared. 4 equals 9 minus x squared minus y squared. So again, switching around, we get x squared plus y squared is equal to 5. Okay, so a little bit smaller. So that's another circle inside of that. So this is z is equal to 3. And I'm going to do one more here. If we let z be equal to 3, we have 9 is equal to 9 minus x squared minus y squared, which is x squared plus y squared equals 0. Well, that's just a circle with radius 0, so that's just a point. So here we get z is equal, oops, this one was 2, sorry. Z is equal to 3. It's just a point there. Now you can kind of see what would happen if we did z equals 4. We'd have x squared plus y squared equals a negative number. Well, that doesn't make sense, right? That can't happen. You can't square two numbers, add them together, and get a negative. So the graph doesn't exist there. So the idea here, at the xy plane going up, this really is just, thing has circles getting smaller and smaller until we make it up to z equals 3. So for this course, this is the type of thing that you would need to be able to draw. Well, let's see if we can transfer that over here to kind of get an idea of what we're talking about. On the xy plane, this thing has a circle of 3. Then we go up one step and it's a smaller circle. We go up another step, it's a smaller circle. And when we're up there at 3, it's just a point. So you can imagine connecting the edges here. What you end up with is kind of that bowl shape I drew earlier, just upside down. All right, so level curves are a very interesting way to kind of get a depiction of what the curve looks like, because we're just picking z values, and you're thinking about for each z value, you're cutting the shape with planes that are parallel to the xy plane. Now you've actually seen this in like your earth science class back 100 years ago from topographical maps. Right, you've seen maps that show elevation curves that kind of look like this, kind of like shown cutting through a mountain, right? So you have some mountain out there, right? And basically they said, well, they cut through it, and everywhere on this curve was at 100 feet. Everywhere on this curve, you're at 200 feet. Everywhere on this curve, you're at 300 feet. It's the exact same concept. You're just, the z direction would be up and down, and you're just slicing the entire mountain at 100 feet, and that's the shape that you would kind of get out of it. All right, level curves are a nice way to kind of picture a three-dimensional shape, but we can expand this upward. Now, we can't draw in 4 dimensions, but we can do level curves for 4 dimensions. If we have a 4-dimensional graph, I'm not going to be able to draw this for 2 reasons. 1, it's really hard to do, and 2, I can't draw very well. But let's say we had w is equal to, I don't know, x squared plus y squared plus z squared. I'm doing my best here. This is going to look horrible. I'm sorry. So if we wanted to do this, here we have 3 independent variables and 1 dependent one. So technically this is a 4-dimensional object. Can't draw that, right? We can only draw in 3 dimensions. But if you look at this, for each one of these, if you let w be different values, so if you let w be equal to 1, that would be a sphere with a radius of 1. So you get a ball here. So we would get a sphere here. Let me go around there. Of radius 1. So everywhere on that sphere, w is equal to 1. And then you plug in another number. Let's say w is equal to 9. So there, that would be a sphere of radius 3. So you'd end up with a sphere like this that has a bigger radius of 3, and you get these surfaces inside of other surfaces. Now, a lot of times you think, well, what would I ever need something like that for? Well, this actually works out really well, kind of the example I gave you earlier. A lot of times, temperature is a function of x, y, and z. So, just for letter's sake, if I were to replace that with a t, say for temperature, then you'd say everywhere on the inner sphere, the temperature is 1 degree. Everywhere on the blue sphere, the temperature is 9 degrees. And a lot of times if you're developing, I know a lot of you guys are engineers, you're developing parts that are in heavily used. Thermal maps like this are something that you're going to want to take a look at to see if you have any parts that might end up melting your machine. So a little bit hard to do it. Most of the time we have computers to do something like this for us. We don't do this by hand very often. But you should be able, at least in your homework, sketch the two-dimensional level curves for three-dimensional objects.